Every modern computational task, from querying a massive database to routing data packets across the globe, relies on systems designed to eliminate structural redundancy. When raw networks contain closed loops, data packets get trapped in endless routing cycles, creating broadcast storms that can quickly crash entire systems. To prevent this, enterprise switches force a chaotic web of connections into a strict hierarchical structure. They mathematically strip away the redundancy until only a specific, highly regulated shape remains. In graph theory, a tree is defined by two conditions: fully connected and completely acyclic. Add an extra connection and you violate the acyclic rule by creating a closed loop. Remove any edge and the structure instantly fractures into isolated components. A tree exists in a state of perfect mathematical equilibrium. It provides absolute connectivity with zero redundancy, making it the bedrock of computer science optimization. This state of equilibrium creates a strict, non-negotiable invariant regarding the ratio of data points, or vertices, to the links between them. This chart tracks the vertex-to-edge ratio. A valid tree containing exactly n vertices will always contain exactly n-1 edges. 5 nodes require 4 edges. 10,000 nodes require exactly 9,999 edges. This gives us the concept of the minimally connected graph. Every single edge acts as a critical bridge. There are no backup routes, and there is no wasted capacity. Highly connected structures, like complete bipartite graphs, where multiple nodes connect to multiple targets, fail this test because they contain hidden cycles. Only a star graph, where one central hub connects outward to individual endpoints, qualifies as a true tree. This strict n-1 constraint guarantees that traversal algorithms will never get caught in infinite loops. It allows software engineers to predict memory usage perfectly and guarantee execution times across massive datasets. Because trees explicitly forbid cycles, finding a specific piece of data inside one requires a systematic algorithm rather than a random walk. This diagram shows a breadth-first search, or BFS. It explores the structure horizontally, level by level. It manages this using a first-in, first-out queue, ensuring all nodes at distance 1 are processed before the algorithm looks at distance 2. By expanding uniformly in all directions, breadth-first search mathematically guarantees the discovery of the absolute shortest path from the root to any target. Depth-first search takes an opposing approach. It aggressively plunges down a single vertical branch as far as possible. Instead of a queue, it relies on a last-in, first-out stack, or recursion, to track its position. When depth-first search hits a dead-end leaf node, it stops, pops its current location off the stack, and backtracks upward just enough to explore the next available branch. This exact backtracking mechanism solves constraint puzzles like the subset sum problem. If an algorithm needs to find numbers adding up to exactly 39, DFS models the include or exclude decisions as a binary tree, dives down a path, and instantly backtracks if the running total exceeds the limit. The choice between a queue and a stack dictates the geometry of the search. A queue forces a wide, proximity-based exploration, while a stack drives a deep, exhaustive search. In physical networks, connections are rarely equal. Fiber optic cables run different lengths, and server links carry different latency costs. We model these variations as weighted graphs. When engineers need to connect all server racks at the lowest possible cost, they compute a minimum spanning tree. This is a subgraph that retains full connectivity across all nodes, but strips away redundant links to achieve the lowest possible total edge weight. For sparse networks with a limited number of connections, Kruskal's algorithm is the optimal greedy approach to build this structure. This visual maps out Kruskal's initial setup. Before touching the graph itself, the algorithm extracts every possible edge and sorts them globally from cheapest to most expensive. This step takes big O of E log E operations and determines the sequence of decisions. The algorithm then iterates through the sorted list, greedily selecting the absolute cheapest connection available and bridging those two isolated nodes on the graph. It moves down the list, but strictly enforces the tree invariant. If selecting an edge would connect two nodes that already share a pathway within the same component, a cycle would form. That edge is immediately discarded. Under the hood, Kruskal utilizes a union fine data structure to track these connected components, ensuring cycle detection happens quickly without requiring a rescan of the entire graph. Kruskal mathematically guarantees that an expensive, chaotic web of options collapses into the absolute cheapest routing structure possible. The exact same mathematical constraints used to route physical cables are used to organize digital data in databases. A binary search tree enforces a strict positional rule. For any given node, every value in its left subtree must be smaller, and every value in its right subtree must be larger. This diagram shows me in-order traversal mechanism. It visualizes a curve tracing tightly around the perimeter of the tree. The algorithmic rule is to visit the left child, output the root, and then visit the right child. By recording each node exactly when the traversal passes directly underneath it, the algorithm perfectly extracts the data following that left-root-right pattern. Because the placement of the nodes was originally bound by the binary search tree invariant, this specific traversal mechanism mathematically guarantees an array in strictly ascending sorted order. Furthermore, the structure allows search algorithms to discard half the remaining data at every single step, moving left or right depending on whether the target value is smaller or larger than the current node. Enforcing the binary search tree invariant converts a slow, linear search into a logarithmic retrieval, allowing databases to process millions of records in milliseconds. When working with these algorithms, it is common to misattribute guarantees to the wrong traversal method. This comparison illustrates the first major pitfall. Assuming depth-first search is useful for optimization. DFS will find a path to the target, but it is often winding. Only breadth-first search guarantees a shortest path tree on unweighted graphs. The second misconception concerns minimum spanning trees. It is easy to assume that different construction algorithms, like Prims and Kruskals, might yield different network shapes, but graph theory relies on a strict uniqueness theorem. If all edge weights in a graph are distinct, the minimum spanning tree is mathematically singular. Regardless of whether you build outward from a single vertex using Prim's method or combine independent edges globally using Kruskal's method, the final structure will be exactly the same. Algorithmic outcomes are entirely directly bound to structural invariance of the graph they operate on. This equation is the core thesis. A tree is simply the enforcement of strict connection without cycles. This single structural constraint powers the rapid execution of breadth-first search, the efficiency of Kruskal's algorithm, and the logarithmic retrieval times of binary search trees. Mastering graph theory is about understanding the strict mathematical constraints that make computation scalable. Subscribe for more rigorous deep dives into computer science.